I'm very happy to be here. It's always a pleasure to discuss with non-mathematicians. I try to do it as much as I can. I think it's important to share with others. You know, mathematics for me is just about understanding. And understanding is a private, an intimate feeling. However, to understand and to enjoy this intimate feeling, you need to communicate with others. You need to use words. You need to use a language. So you will have necessarily two aspects in mathematics. One is very personal, emotional, and inner. And the other one is from the outside. It necessitates a language to communicate. So I want today to express this very naive idea for mathematicians that we should make a distinction between two kinds of simplicities. Something could be very simple for me, in my mind, in my way of feeling mathematics, and very difficult to express, to write down in a mathematical paper. And conversely, something can be very easy to write down, to express in a short way using English or French or whatever, and nevertheless being very, very inaccessible to my mind. So this is basically what I want to say today. This is something which I believe is classical, but sometimes we mathematicians, we mix these two ideas. We keep forgetting that writing a paper is not the same thing as understanding it. So let me begin by some very, it's an old memory that I have. A long time ago, when I was a student, I was reading a book by a very famous French mathematician, Jean-Pierre Serre. Here's the cover of this book. And for many years, I've been convinced that the title of the book was a joke. Because, you know, how can it be complex and simple at the same time? And for mathematicians, this word complex and semi-simple are used in totally different meanings. So complex means complex numbers, and semi-simple means a sum of simple objects. So during many, many years, I was really convinced it was a joke. And Jean-Pierre Serre is, again, a very, very famous mathematician. He's 85 now. And now that I have the opportunity to speak with him, one year ago, I dare asking him the question, is it a joke? And he told me, what? Why is it funny? So he never observed that the title was putting different words in the same. It was not a joke for him. Because mathematicians use words as words. And they don't want to use the words with their meaning. You know, there's a famous sentence of Hilbert that you could change all words in mathematics. And instead of line, you would say a chair. And instead of point, you could say a bottle. And you could say that in between two bottles, there is one chair. And mathematics will be unchanged. This is the point of view of Hilbert, which, of course, is not at all my point of view. So this is the first aspect. There is, in mathematics, there is an external simplicity which is conveyed by a language. And this language is kind of artificial. It is made out of words which are not really subject to meaning. So basically, this difference between the two aspects, one could, oversimplifying the picture, one could say Hilbert was on the logic side, say writing words, without looking for meaning to these words, and Poincaré was on the intuition side, say from the, of course, you know my favorite part. You can see this is a chocolate. You know, Poincaré was so famous they would use his photograph on chocolate. And do you know one mathematician today whose picture could be on chocolate? Anyway, so this distinction between inner and outer is precise. This is outer and inner. Hilbert was basically focused on transmitting mathematics, and Poincaré was focused on understanding mathematics. Before we start, and since I'm the first speaker, I thought it could be a good idea to open the dictionary at the word simplicity and complexity. And I can tell you, I don't know, because you're very scholar and learned people, so maybe this is obvious for you, but I would say that maybe it's not obvious for, it's more obvious for French-speaking people. Simple comes from plier, to fold. Something is simple, it is folded only once. And it's complex if it's with many folds. And to explain something is to unfold it. So I think it's something we should keep in mind. Complexity, simplicity is related to folding in all directions. You have the word to ply in English, no? Is it this? To fold, ply. And what is to plate? Plate also? Okay. So the first, if you look to the outer simplicity, using terminology, using words, it is kind of obvious that a measure of complexity is the so-called Kolmogorov complexity. Kolmogorov, when was that? I think in the 50s, had the idea of defining complexity as saying that the complexity of something is the length of the shortest explanation of that something. How many words do you need to describe something? And this length will give you the complexity of this object. So here's an example, a very simple example. If you take this black square by Malevich, 1915, I can describe it to you with, let's say, 5 or 6 sentences. It's a square with such size, and it's white, and inside it there's a smaller square which is black. And I could give the precise blackness and whiteness of the two squares. So this is a very simple object. Now, this is due to Malevich, and now let me show you my own art object. This is totally random object. So it's a square, and in each dot, I asked my computer to put a yellow or orange dot. And it's totally random. So if you ask me to describe it to you in detail, the only possibility that I can do it is to describe it dot by dot. So if you want me to describe it, I will need a very, very, very long sentence. This saying the first point is yellow, the second one is red, etc., etc., etc. So it will be a very long description. So once again, this is a complex object, and this is a simple object. This is in Kolmogorov's terminology. Now, here's a third object, which is very famous in the mathematical world, which is the Mandelbrot set. It looks complicated, and it is complicated for all mathematicians, but for Kolmogorov, it's a very simple object. I mean, in order to produce this picture, maybe the computer worked a long, long time. Maybe it worked days or weeks or whatever. But the program to describe the Mandelbrot set is 2 lines long. So from the Kolmogorov point of view, this object is very simple. So this is the first concept of simplicity, this outside simplicity, the length of what you need to describe it. Clearly, it is not satisfactory. I mean, for me, I don't want to consider this as being something simple. This is complicated for me. It's made out of many folds. Let me give you an example, again, a personal example of a simple linguistic thing which is complicated, or at least which was complicated to me when I was a student. Again, I will take the example of Jean-Pierre Serre. Jean-Pierre Serre wrote a wonderful book for students on number theory called Cours d'arithmétique. And this book, I opened it when I was, I think, 19. And let me show you the first page of this book. This first sentence of the book, l'intersection. So I put it in English, in French. Let me explain why in a moment. So I opened this book, and I can tell you that I spent 2 full days on one sentence. And looking back to these 2 sentences, or to this sentence, it's only one sentence. Looking back to this sentence, I see now that this is just perfect. There is nothing to change in it. Every single word, even the smallest, have their importance. For example, I put it in French because I wanted to show you the English translation, but the English translation is so bad. I mean, the French of Jean-Pierre Serre is so good and so efficient and so elegant and so simple. It's so simple that I don't understand it. So see, even the smallest words like d'un corps cas en, these 2 letters, en, is fundamental in this. Everything, every single word is fundamental in this definition. From the Kolmogorov point of view, this is very simple. But as a student, at the time, I knew almost nothing about these anneaux intègres and all these things. It looked so complicated. But finally, after 2 days, when I grasped it, I was so happy that all of a sudden, I could understand it. And so from Kolmogorov's point of view, it's simple. And for me, it's not simple. And I guess for many students, it's not simple. Let me give you another example. Again with Jean-Pierre Serre. I take this example of Jean-Pierre Serre because Jean-Pierre Serre is really probably, or maybe, I don't know, the most famous French mathematician. He's like, we mathematicians in France, we consider him as God. His writing is so nicely. Most of my students, when they write their PhD, and when they write badly as usual, I say to them, go to the library, open any book of Jean-Pierre Serre, and try to copy. And this is really the best elegance and efficiency. Here's the example I wanted to mention. Long time ago, maybe 15 years ago, I was giving a talk in the Bourbaki seminar. And I was describing a construction in dynamical system due to Christina Cooperberg of a very fascinating counterexample to an old conjecture of Seifert, constructing a vector field on the 3-sphere with no periodic orbit. This is a wonderful, simple idea, really wonderful. So I prepared my talk, and I prepared pictures. And let me show you one of the pictures that was in my talk. I showed this picture. This is an object. I don't want to describe it for you now. This is not the point of this talk today. So I gave my talk. I explained things. I was, you do this and this. And after the talk, well, I think it was kind of a success. People were happy. And Jean-Pierre Serre came to me and said, that was interesting what you said, but I have a question. And he said, would you consider this as a theorem? In other words, he was considering that because of the fact that I was using pictures and not words, I was disqualified for transmitting mathematics. And my feeling is that and this is not only my feeling, you will see in a second, that pictures, and more than pictures, even movies, should be incorporated to the world of mathematics as genuine tools of proofs, of not for the fun, for the truth, I mean, for presenting mathematics. So let me explain something to show that I'm far from being the only one to think this way. You will discuss in this meeting the 24th Hilbert's problem, but I want to discuss today the 0th Hilbert's problem. You know, when Hilbert gave his famous lecture in Paris on problems for the future of mathematics, this paper contained 23 problems, and it was preceded by some introduction, a general introduction on what is a good problem, what is interesting in mathematics, where should we go, etc., etc. And in this introduction, I consider that there is something fundamental in this direction, and I want to show it to you because I think it's really like a fundamental question for today in mathematics. And the point is that we should incorporate pictures as genuine tools for understanding and transmitting mathematics. So here's an extract from this introduction of what I call the zeroth problem. To new concepts correspond necessarily new signs. These we choose in such a way that they remind us of the phenomena which were the occasion for the formation of the new concepts. So the geometrical figures are signs or mnemonic symbols of space intuition and are used as such by all mathematicians. Who does not always use, along with a double inequality, A bigger than B bigger than C, the picture of 3 points following one another on a straight line as the geometrical picture of the idea of between? Who does not make use of drawings of segments and rectangles enclosed in one another when it is required to prove with perfect rigor a difficult theorem on the continuity of functions or the existence of points of condensation? Who could dispense with the figure of the triangle, the circle with its center, or with the cross of 3 perpendicular axes? Or who could give up the representation of the vector fields or the picture of a family of curves or surfaces with its envelope, which plays so important a part in differential geometry, in the calculus of in the theory of differential equations, in the foundation of the calculus of variations, and in other purely mathematical sciences? The arithmetical symbols are written diagrams, and the geometrical figures are graphic formulas. And no mathematician could spare these graphic formulas any more than in calculation, the insertion and removal of parentheses, or the use of other analytic signs. The use of geometrical signs as a mean of strict proof presupposes the exact knowledge and complete mastery of the axioms which underlie those figures. And in order that these geometrical figures may be incorporated in the general treasure of mathematical science, there is necessary a rigorous axiomatic investigation of their conceptual content. Just as in adding two numbers, one must place the digits under each other in the right order, so that only the rules of calculations, the axioms of arithmetic, determine the correct use of the digits, so the use of geometrical signs is determined by the axioms of geometrical concepts and their combinations. So, Hilbert is asking for a language of pictures. There should be ways of presenting mathematics in a simple way, without using only letters, languages. You know, I was recently discussing with people from choreography, and they have some kind of same problem. They are looking for notation for choreography. How would you denote choreography? They have several ways of doing it. One is called Benesh language. Yes, there are many possibilities like that. And they have exactly the same problem. Why should we restrict ourselves to a linear, totally ordered language in order to describe mathematics, since we are not linearly ordered in our mind? Or at least I am not. The agreement between geometrical and arithmetical thought is shown also in that we do not habitually follow the chain of reasoning back to the axioms in arithmetical any more than in geometrical discussions. On the contrary, we apply, especially in first attacking a problem, a rapid, unconscious, not absolutely sure combination, trusting to a certain arithmetical feeling for the behavior of the arithmetical symbols, which could dispense with as little in arithmetic as with the geometrical imagination in geometry. As an example of an arithmetical theory operating rigorously with geometrical ideas in science, I may mention Minkowski's work, Die Geometrie der Zahlen. So, you know, this is kind of unusual in the way we think of Hilbert. He's praying for a better use of pictures. Now let us go to Poincaré. Poincaré is really not interested by language. I mean, he is not interested by all which is outside mathematics. He is more interested by the inside of mathematics, by the intuition. And he has a very nice comparison. He says that we should not compare mathematics with a game of chess. You know, you can easily learn the rules of the game. You can check if a game is fulfilling the rules, but it is clear that you are not a mathematician if you only know the rules of the game. You are not a good chess player if you only know the rules of the game. You need some global understanding of the picture, and from that point of view, logic is totally useless. So here's this comparison. If you are present at a game of chess, it will not suffice for the understanding of the game to know the rules for moving the pieces. That will only enable you to recognize that each move has been made conformably to these rules, and this knowledge will truly have very little value. Yet, this is what the reader of a book of mathematics would do if he were a logician only. To understand the game is wholly another matter. It is to know why the player moves this piece rather than this other, which he could have moved without breaking the rules of the game. It is to perceive the inward reason which makes of this series of successive moves a sort of organized whole. This faculty is still more necessary for the player himself, that is, for the inventor. This reminds me of something. When you use your iPhone to look at a direction, you use Google Maps. It's amazing how quickly Google finds the best path from A to B. And basically, this is what we try to do in mathematics. We want to go somewhere, and we look for the best path. And it's possible. And this is the same with Google. And I don't know if some of you have looked at the algorithm that Google is using, Google Map is using. It's called A-star algorithm. It is a very, very clever way of finding your way in an unknown country. So I really suggest that you have a look at this software. This is really a clever way. It could be used maybe to an analogy to understand better how mathematicians are working, how we try to move forward, and from time to time we have to move backward to take another direction. Okay, so what I want to say is that really this connection between the outside and the inside is not good for the time being. We should improve it. We should write mathematics in a different way. Hilbert is suggesting that we should use pictures. I would even add that we should use movies. Let me give you an example. There is this theorem of Smale that one can transform a two-sphere, when you can invert it in three space. Anyway, it's a theorem which is not easy to prove, and the proof is formal and rather not easy to understand. However, there was, when was that? 20 years ago, I think, maybe 25 years ago, Silvio Levi, Thurston, and somebody else, I forgot, they created a movie called Inside Out. And this movie is really remarkable. It is 15 minutes long. And you see what's happening. And of course, it is still not possible to qualify this as a proof. But we are very close to a proof. And if we follow the advice of Hilbert, we should create the rules that transform this into a genuine proof. And one should be able, maybe tomorrow or maybe in 10 years, to publish proofs using movies. As soon as they are certified by some certification that I still don't know how to do. Another thing that I consider important is that we should think of the way we write mathematics. During many years, we have written papers from A to Z, and it is well known that no mathematician would open a paper or a book and start by the beginning and go to the end. We go, we jump, we come back, we go some other place. So we should be able to write mathematics, and not only mathematics actually. We should be able to write mathematics in a nonlinear way. But today it is possible. Computers, e-books, all these technologies are proposing for us ways of doing it. So why don't we do that? I think it's time to create papers which are not just standard papers going from A to Z. Next week, I will start some exciting experience for me. We have a group of 18 mathematicians, and we plan to write a book on algebraic topology, let's say a graduate course in algebraic topology, but we want to do it this way. We don't want to write a book with pages. We want to write a book which will be completely electronic, and in which you can travel in a way which is adapted to the reader. So this requires some thinking before we start. Anyway, so we have to try to adapt the outer way of describing mathematics to the inner way of the readers. Okay, so let me, you know this, this is this crazy idea that comes from Erdős, that somewhere in the heaven there are some jewels, some wonderful proofs, and we should go towards these beautiful proofs, simple proofs, elegant proofs. And this book contains a few hundreds of those jewels. I'm not really convinced. I don't know how many of you read this book, but some of the theorems inside this book are really wonderful, but I try myself to read it, and I can guarantee that for most cases, not all, but most cases, I read them, they are just wonderful. And then you close the book, and let's say 1 year later, I had forgotten them. So this is bad sign. I mean, when I understand something, by definition, I don't forget it. So this concept of beauty here is very, I think is not the correct one. The simplicity is not the correct one. Anyway, so let me finish by explaining something. When I was a student, I was taught, I don't know if this country, but I was taught as a student that you should never give a talk, never, 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 without stating a theorem. So I decided that maybe I could spend the last minutes of this talk mentioning a theorem that I understand. And I think I will never forget it. I will not give you the proof, but, and not only that, I want to explain this theorem because I believe it tells you something about the way maybe the brain is understanding mathematics. I'm not a neurobiologist, I have no idea about psychology, but I think it's something fundamental. It's a simple, fundamental idea, and I want to share it with you. So the thing is to try to discuss how we can understand large networks. So here's a picture of a network of neurons. You have hundreds of thousands of neurons, and they are connected in a way that you don't really understand. And you want to describe this structure. Do you know how many neurons I have in my brain? 100. I thought my brain, only 10 billion, my brain. Okay, I think it's 10 billion, I think. Anyway, 10 or whoever. Here's a picture, I think this is a vague picture of internet. How many HTML pages in the world? 10 billion. So the number of pages in internet is approximately the same as the number of neurons in your brain. The difference is that the connectivity is different. The average connectivity between two sites on internet is, I think, 20. A typical web page is connected to 20 other web pages, but a typical neuron is connected to 10,000 neurons. So it's much more connected in my brain. Another main difference is that internet is going faster than my brain, because connection in internet goes through electricity, through the light, and connection in my brain goes through the biological, chemical reaction, so it's much slower. So my brain is slower but better connected, and the internet is more connected but faster. Anyway, I think it's good to compare these two structures. How can we understand these kind of things? They are huge, very big, 10 billion things. So here's a theorem I want to mention. It's a theorem of Zemeredi. It's called the Zemeredi regularity theorem. You will see it's a very general theorem which is true for all networks and which carries the idea that all networks, how big they could be, they can be understood in finite terms, so to speak. Let me explain that. So here's a network. A network is just a bunch of points that could be whatever you want, and some of them are connected by links or edges. And you want to draw pictures of that. So of course, this picture is reasonable because the number of dots is rather small, and it's totally impossible for me to draw a picture of a complex network like internet. So here's the question, how could I draw internet? what could be a good picture of internet? Of course, the number of pages of internet in the world is so big that it's impossible to draw it on the board. I mean, there are more points on internet than pixels on the screen. So no way of drawing the picture. So how can I draw a fairly accurate picture of large networks? And this is what this theorem of Zemeridi tells you. It's possible to do things. So let me express that. Here's a network. You have points and dots. You have dots and you have links between them. And the idea is that we want to group vertices. We want to group these dots into several groups, A1, A2, A3, A4, A5, and we want to somehow to collapse them. And we want to replace the complicated picture having many dots to a much simpler picture with less dots. Instead of having maybe 20 dots, you will have only 5 dots. The new dots will be the big ellipses. You have a new dot will be A1, A2, A3, A4, A5. And I will connect 2 dots, A5 and A2, accordingly to the connections between the dots in the, you will see that. Okay. Now let me give definition and then state a theorem, since this is my job. You know, my job is to state and prove theorems. So here's a picture. You have 2 sets, A and B. Inside A and B, you have subsets X1 and Y1. X1 is a subset of A, and Y1 is a subset of B. And then you define some numbers. The first number, you call it the density. The density D of X1, X2. Well, you count how many edges go from X1 to X2. The total number of connections going from some point of X1 to some point of X2. And you divide it by the product of X1, by the number of points in X1, times the number of points in X2. So it tells you somehow the probability of connecting 2 points in X1 and X2. And then you say that AB is epsilon regular if every time, forget the beginning of the sentence, for every subset X1 in A and Y1 in B, the densities D of X1, X2, and the density D of AB agree up to epsilon. So if you have that, that means that A and B are very well connected. I mean, any part of A and any part of B, any part of A and any part of B are connected basically in the same way. So if this happens, you say that AB is epsilon regular. And now I can state the theorem of Zemeridi. The theorem says that every graph, every network, given epsilon, can be approximated by a finite graph with a number of points independent of the original size of the graph, but only dependent on epsilon. So let me state correctly the theorem. For every epsilon, there is mm, such that every finite graph can be partitioned in n parts in such a way that n is between m and m, and all the AIs have approximately the same size. Oh, the second, the mistake there. Approximately the same size up to epsilon, and among the n square pairs, at least 1 minus epsilon n square epsilon regular. So this means that whatever is the size of the original network, you can approximate it by a finite small graph, which gives you almost all the information you want about the connectivity inside the original network. Let me show you one example. Just one example, and I'll finish with this. This is a famous picture, old picture. This is a picture of internet. So this picture is, of course, very naive. It's a naive image of internet. It tells you that you can, roughly speaking, decompose internet into several parts. You have the SCC, that means the strongly connected core. It's about 1/3 of the total internet world. This is the part in which everybody is interested with everybody. It's highly connected. Everybody connects everybody. Then you have the out, which are the pages where everybody goes and nothing goes from them. And you have the in part, about the same size. They are the pages that are not interesting for everybody, but which are interested by everybody. And then you have some disconnected components, maybe I don't know, the stamp collectors, and then you have these little tubes and these dendrites, etc., etc. Anyway, this theorem of Zemeredi, in a word, explains that any network, even very big, like the internet network, can be described in such a way with a simple picture. It doesn't tell you exactly the structure of the graph. It doesn't tell you exactly the structure of the network, but it tells you something about the global picture of it. And if I wanted to mention this theorem to you is, first of all, because this is an example where if you look for the proof in mathematical papers, it is complicated. I mean, it is complicated, but I understood it. And for me, it's simple. I think I will never forget the proof because I understand it. And this is the exact opposite of this one page, one line of Jean-Pierre Serre, which was so short that it took me days to understand it. This is the exact opposite. Here, the proof that you find in books is very long, but once you get it, you say, well, I understand it. Why did they write such a long book on this? Thank you very much.